Now let's look at the intersection of sets. So the intersection of sets A and B, which is written like this, is a set of elements in common to both set A and set B. So notice the the notation. It's like a little upside down U kind of. It reminds me of an N in a way, so it kind of looks like an N, which helps me correlate it with the word intersection. So that's how I remember it. And what happens is you want the elements that are in common to both sets. So for the first one here, I'm just going to kind of label the first set as A and the second set as B, just to make the notation a little bit easier. So I'm going to look for elements that are in common to both sets here. So I can just go through one at a time. Do I see a 7 in both sets? I don't. I see an 8 in both sets, though. I don't see a 9 in both sets. I do see a 10 in both sets. And I don't see an 11 in both sets, or a 6 or a 12. So I just go through one element at a time and see what's in common. So here we have two elements in common, 8 and 10. Now for the second example, if I go through my elements, 1, 3, 5, 7, 9, and 2, 4, 6, 8, they have absolutely nothing in common. So they have nothing in common with each other. So their intersection is no elements, and we write that as the empty set. Now for the next example, so we have the same set for A, but we're intersecting with the empty set here. So we're looking at A intersect with the empty set. Well, the empty set has no elements in it. This one has the elements 1, 3, 5, 7, 9. So really, again, there's nothing there. So we're going to use the empty set again, in this case, as our notation. So when we're intersecting with the empty set, your answer there is going to be the empty or null set as well. Now, the union of two sets is the opposite idea. So the union of the two sets, and you're using this notation. So this one looks more like a proper U. So I think U for union, right? Your symbol kind of looks just like that U. Is a set of elements that are members of set A or of set B or of both sets. So as long as you're in one of the sets, then you're in the union. So we're basically uniting the two sets together. So for the first one here, again, I'm just going to use A and B just to work with that notation a bit. So I'm going to just unite these sets. I'm going to combine them both together, but I don't want to repeat anything. So you don't have to go in order, although a lot of times you do see values in order. So I see a 6, I see a 7. Now I see 8 in both, but I don't need to write it twice. I'm just going to write it once. I see a 9, I see 10s, so I just write 1, 10, 11, and 12. And again, the order of the set actually doesn't matter. So what you could do is just write one set first and then just write anything missing still. I'm using the second set. Although you will see that most of the time we do tend to write them in order, but it's not required. So here, again, I see I have numbers 1, 3, 5, 7, 9, 2, 4, 6, 8. I don't have any repeats, so I'm just going to combine that all together. So I have 1, 2, 3, 4, 5, 6, 7, 8, and 9. And then for my last one here, again, this one looks a little bit different. I guess I should probably write it like this, right? A union the empty set, since we know specifically what we're looking at here. Now we're uniting these two sets together, but the empty set doesn't have any elements in it. So it's not going to contribute to the union. So I'm just going to list the 1, the 3, the 5, the 7, and the 9. Okay. So here's just kind of a little summary of when you're working with that null or empty set. If you're taking the intersection, your answer is always going to still be that empty set. If you're taking the union, your answer is going to be the original set. So opposite ways or opposite things are going to happen here, but this is always going to be the case. So no matter what A is, take the intersection, you're going to get the empty set. And if you take the union, you'll get that other set A, which we saw in these examples. And that's because the empty or null set doesn't have any elements. So it's, for the union, it's not contributing. And then for the intersection, there's nothing for it to intersect with. So that's why we have those answers here. All right, now let's do some examples using these operations. And what you want to do is just think of them like little puzzles and take it step by step. If you do have parentheses, just like with order of operations and PEMDAS, you do parentheses first. So we don't always have parentheses, but if you see that, then that is telling you to do this step first. So notice in part A here, I'm looking at parentheses A union B. So because this is in parentheses, we're going to do this part first. So what I want to do first is find the union of A and B. So here are my sets that I'm working with. I have my universal set, A and B, and I want to find the union first. So for that, I'm going to combine the two sets together. So let's see, I have a 1, I have a 3, I have a 7, I have an 8, and a 9, and a 10. Now, this mark here, remember, is the complement, which is like a not idea. So once we have the union, now we want to find the not version of that. So I want the answers that are not the union. Okay. So I go up to my universal set here, right? Because the universal set is your overarching set. It contains everything. And I want the values that are there, but not in the union of A and B. So what numbers are still missing? I have a 2 here. I can use the 4, the 5, 6. Now here I have 7, 8, 9, 10. So that's going to be it. So these are the values that are not in A union B. Now here I don't have any parentheses, but a good rule of thumb is if you're finding an intersection or union and you have complements as well, again, unless there's parentheses, which tells you to do something specifically first, I would find the complements first and then find the intersection. That's the easiest way to do it. So I'm first going to find what A complement is. So again, I want all the values in U that are not A. So I have a 1, 3, 7, and 9 in A, so I'm going to take those away. So I'm left with 2, 4, 5, 6, let's see, 8, and 10. And then I'm also going to do the same thing for B. So I want to find all the values that are not B, right? So the complement of B. So we're going to go to the universal set, but I want to take away the B values. So I have 1, 2, 4, 5, 6, and 9 left over. Now I want to find the intersection of these sets. So the intersection of these sets means that the element is in both. That's where we overlap in the Venn diagram. So what elements are in both A naught and B naught, or A complement and B complement? I see 2, I see 4, I see 5, I see 6. And that looks like it. So I don't see any other numbers that are intersecting there. So I'm just going to go ahead and write that as my final answer. So A complement intersect B complement is 2, 4, 5, and 6. Now, a lot of times you'll hear me say like A naught, B naught. That's just kind of like shorthand slang for A complement, B complement. So if you're watching videos, myself included, or you're looking online and you hear A naught, B naught, it just means the complement of A and the complement of B. Sometimes we get a little bit lazy and say that instead. All right, let's do a couple more examples again with these Venn diagrams and these set operations. So here you have your Venn diagram. You have your universal set, which includes everything. You have your set A and your set B. And again, you have this overlapping piece in the middle. So those are elements in both sets A and B. And then you just have elements in each part. And again, you see Roman numerals 1, 2, 3, and 4 here. Those aren't necessary, but a lot of times we label the different parts. It just makes it easier for us to talk about them. So you'll see that sometimes as well. So the Venn diagram includes interesting numbers, it says. Use the diagram to determine each of the following sets. So that's what we're going to do right now. All right, so first one, A union B. So remember, your union basically means put everything together. So I want all elements of A and B. So if you're looking at the regions here, that's going to include regions 1, 2, and 3, right? So it includes everything in A, which includes 1 and 2, includes everything in B, which is 2 and 3. We don't need to write the numbers in 2 twice. We can just write them one time. So I have pi e root 2 root negative 1 e to the pi I 10 to the 100, and then the last one I can't even read. Okay, so that one here, it's very hard to read here. It's just notation that we have for how to count infinite sets, like the cardinality for infinite sets here. So it uses a Hebrew letter. So it's a little bit hard to read, but that's there too. All right, so now we're going to do A union B not, or complement. And we're going to do parentheses first. So you already have A union B from right here. So we want the complement of this, meaning we want everything that's not this. So look at my overall set here, and I want everything in the universal set that's not these. So there's two numbers here that are not included, or sorry, one number here that's not included, and it's the 666. So that would be my answer here. So it's that region 4. So everything that is not in the union of A and B. Do it right here. So now I want A intersect B. So this is my overlapping region. So this is region 2 right here. This is your A intersect B. Okay, it's that overlapping region. So what I have there in common is root 2 and root negative. And then for part D, we're looking at that intersection, but the complement of it. So we want the opposite or the not, right? So everything else that is not the intersection. So I'm going to list all the other elements that are not in the intersection, but are in the universal set. So I have that pi, I have the e to the pi I, 10 to the 100. And then also, sorry, I'm missing it here, 666 at the end. All right, so it's all the elements that are not included. Now, E and F are a little bit different. So here we're looking at the complement of A intersecting with B. So before I can find this intersection, I do need to find the complement of A first. So I'm going to just do that up here. So the complement of A is everything in the universal set that's not in A, right? So this is not A. So I have this left, this, and this one. And I want to intersect that with B. So now I'm just going to write up here. I think it's easier to see. All right, so in set B, I have the root 2, the root negative 1, and then these values here. And I want the intersection, so I want the ones that are in common here. So I see I have 1, 2, and 3 things in common. And then finally, F is going to be very similar, but instead we're going to find B not first. So I'm looking for a union, but I need to find that B not first. Again, I wouldn't try to rush and do this all in your head. I think it does help to write out the different parts if we don't have it already done. So I do not have that complement of B yet, so I'm gonna just take my time and write that out. So it's gonna be everything that's not in B. So I have pi, I have E. So all this is in B, I can't include that, and then I have the 666. And I wanna make that into a union with A. So these are my elements in A. So here's my A, those are my 4 elements, and I want to do a union, so I'm going to combine them all together, but I don't need to repeat anything. So I have the pi, I have the E, I have the root 2, root -1, and 666. So again, just really working with those different sets, taking our time there. So don't rush these. Like I said, particularly once you start throwing in complements or parentheses and things like that, just take your time. So for these, I personally would not try to do this in my head and just try to figure out what A naught is in my head or complement of A is. I would do this. I would take my time, write out what the complement of A is first, then find that intersection with B. Same thing here. I would write out the complement of B first, then find that union with A. It's much easier to use the roster notation than it is to go right to the final answer. Now, we can also talk about sets in words, right? So we talk about word form or sets having more meaning. So set operations and Venn diagrams provide precise ways of organizing, classifying, and describing the vast array of sets and subsets we encounter every day. When describing collections, the word or refers to a union, the word and refers to an intersection, and the word not refers to a complement. So when you see words or, you want to think union. When you see and, you want to think intersection. And when you see not, you want to think complement. So let the universal set be the set of U.S. Hispanics. Let A be the set of U.S. Hispanics who speak English at home. B, the set of U.S. Hispanics who speak, A is who speaks Spanish at home. B is who speaks English at home. And then we're going to consider the circle graph showing languages spoken at home on page 82, which gives the following information. So if you go to page 82 in your book, they do have a pie chart there, which breaks down these percents. And they just give you this information here. So check out page 82, just to kind of a nice review of a pie chart. And they give us these percents here. But what we want to do is create the Venn diagram. So first of all, we got to start with our universal set. So remember, our universal set is a set of U.S. Hispanics, like all U.S. Hispanics, right? So it includes everybody. Now, based on this, we see that 43% speak Spanish at home, 32% speak English at home, 23% speak both at home, and 2% speak a different language at home. So we want to create this Venn diagram. And let's do some colors. We'll just use red for Spanish speakers. So what you could do here is you could use A, because we've defined A is the set of U.S. Hispanics who speak Spanish at home, or if you find it easier, your book writes in the word Spanish here instead, which maybe just help to visualize it. And you also have some speakers who speak English. Let's use orange for part B. Now notice that you have some people who speak both languages. So those circles are going to overlap, but they're not the same set. So you do have some who only speak Spanish in the home, some who only speak English at home, and then some who speak both at home. So those two different sets are going to overlap, but they're not going to be the same. They're not equal. So this is set B. So this is your English speaking set. And then we have 2% that speak a different language. So if I'm filling in these percents, what it's going to look like is this. So we have 43% speak only Spanish. So that's this region right here. We have 32% speak only English. That's this region. Now, those who speak both languages at home, that's this 23% in the middle. Now, where's the other going to go? Well, the other is still part of the universal set, right? It's just these people speak a different language, right? They don't speak English or Spanish at home, so they speak a different language. So that 2%, what we can do, again, we usually tend to use the corners, so we can just write that 2% here in that fourth region for those who speak a different language at home. So this is a way to take that pie chart given on page 82, which gives us the percents, and turn it into a Venn diagram. So we can see there's a 23% of people who overlap, but then everybody else has distinct languages that they speak at home. And one final example here, the cardinal number and the union of two finite sets. So there is a formula for the cardinal number of the union of two finite sets. Remember, the cardinal number is how many items are in that set. And it's a little trickier than you maybe would think. And if you're trying to find the cardinality for a union, you actually have to be careful. You can take the cardinality of the first set and add it with the cardinality of the second set. But the problem is a lot of time we have an overlapping region, just like we do here. So if we take the cardinality of A and add it with the cardinality of B, what's happening is that overlapping region is getting counted twice. You're counting it once in A and once in B, but actually those people in the middle don't need to be counted 2 times. They should only be counted 1 time. So what we do to fix that is we subtract however many are in the intersection of A and B. And that's how you find the cardinality of the union of two sets. Particularly if it's a difficult one to find. Like if you can just, for instance, A union B here, I can find this cardinality very fast because I can just count the elements, right? 1, 2, 3, 4, 5, 6, 7. So if I have the union already, you can still just count it. But if I don't have it specifically written out in roster form, I can still find it using the other cardinalities first. So here's a great example of that. So some of the results of the campus blood drive survey indicated that 490 students were willing to donate blood. So going back to that survey on campus for those who are willing to help out with the blood donations. 340 students were willing to help serve free breakfast, and 120 students were willing to donate blood and serve breakfast. So how many students altogether were willing to donate blood or serve breakfast? So really I'm looking here for sort of the total students participating. That's really what I'm trying to find, right? The total students are participating. But I have 120 who are in both categories. So I really need to make sure I don't double count here. So I can use this formula. So we're going to let A be the students who donate blood, and B be the students, or the set of students who serve breakfast. So I'm just kind of using a shorthand here for our sets. So for the union of these two, that's how many students donate blood or serve breakfast. I look at how many students are donating blood. Well, 490 students are willing to donate blood, plus however many students are serving breakfast, which is 340, minus the intersection. So in this case, these are students who donate blood and serve breakfast. Remember, you can think of that word "and" as an intersection. So that's this group right here. This 120 students are doing both. So we're going to subtract out that 120 at the end. So you end up with 830 minus 120, which is 710. So there are 710 unique students who are participating in this event, okay? And again, notice this word "or" here. "Or" refers to a union. So that's why we can use this formula. We're talking about "or." So how many students who serve breakfast or who donate blood. So we have to make sure we don't double count those who are doing both. So we can use this formula here, and we see that there are 710 unique students who are either going to donate blood, serve breakfast, or do both.